Dexter will be the ones giving your lesson today. Dexter, you there?
Yes.
All right.
Hello.
So let's get right into it. So if you haven't signed into your Onshape account already, please do and let us know in the chat when you have done so. Looks like someone's joined. We'll give them some time to make sure they're signed in and all that. All right, so hopefully everyone's signed into Onshape by now. Uh, I guess first let's get on with the actual lesson for this part, because we'll be doing this class sort of differently from normal. We'll be sort of like, or it'll be two parts, kind of. You'll see. It'll make sense. But yeah, so then we'll be like finishing up the gearbox from last class. We'll do a quick Q&A and like recap on like why we did certain things to the gearbox, like why this is done in this way, stuff like that. And we're also going to go over gear ratios. And then later on, we are going to have the wonderful Dexter show you how to design a West Coast Drive chassis. Very fun.
Ooh.
All right, so gear ratios. What is a gear ratio? Basically, say you're trying to make something turn, and it's connected to a different axle. You probably already know, because we've already been designing a gearbox since last class. Yeah, you would probably want to use gears. However, um, like, what do different size gears do? And like, why is it important that, oh, maybe I want like this really tiny gear on my motor, and I want the super big gear on my drive axle? And like, this is important because like, okay, so say I want, or so say I have a motor. It's pretty small and it's not too strong, but it turns like super fast. However, I am trying to use this motor to power a robot. A robot is pretty heavy and it doesn't need to go all that fast. Like, or at least not all too fast compared to the like free speed of the motor. Um, so it, I, I think we might have briefly gone over this, but not in too much detail. Um, so if I have like a super small gear on my motor and like a larger gear on my drive axle, like when the smaller gear turns once, or it might only turn the bigger gear like a fourth of a rotation or something like that. So that would be an example of this bottom thing here, the 4-to-1 ratio, like more torque. So basically, a smaller gear powering a larger gear, the larger gear is going to turn far slower than the smaller gear. However, it's going to be significantly stronger, which is very nice if you're trying to like move something pretty heavy, but you don't need to move it super fast. However, if you're using a larger gear to turn a smaller gear, then like one rotation of the large gear will make the smaller gear turn like 4 times, maybe. That's a lot. So yeah, it'll start going pretty fast. However, that does come at the expense of um, it kind of starts to cut into how strong it is. So it doesn't really like you won't be able to like move mountains or anything. And like a 1-to-1 ratio usually just means like, oh, this gear is the same size as this gear, so yeah, there's no change in like torque, no change in speed. Um, but yeah, so gear ratios are pretty important like everywhere. And it's like for a car, the actual motor for a like so the window in a door, it's this really tiny motor. You could probably stop it by just grabbing it. However, it moves that like massive piece of glass up and down, and you can't like force it back down even if you tried to, because the gear ratio is so heavily geared for torque, that it's just so strong, even though it's this really tiny motor. Um, so anyway, now that we've gotten that covered, we'll be going back to the gearbox creation. Um, so we've more or less created the plate. I am going to go over a couple other things that I just forgot to do to the plate. And then since we still have to create the holes, I have to create the holes in the plate for like the bolts and stuff to go through. There will be a couple, or there will be a couple other parts that I can't get through MKCAD, so I'll have to create those. That would be a standoff and an imitation of Thunderhex shaft, um, which we thought they had, but apparently they don't. So that was a fun search. And then yeah, so once we've done that, we can import the parts we need, and then we can mate all the parts together. So I'll just go back over here to session. Oh, it signed me out. I think this is the account I use. All right, so um, this is the plate as we left it last time. There's still a couple problems with this that you can see fairly quickly, because like, oh, like that's a sharp corner, that's a sharp corner. These corners, they're not too realistic, and we haven't fixed them since last time. So I'll go into the sketch now. Let's see. I made that a 0.1 inch radius, a 0.2 diameter. And then I need to get this corner here, this corner, these corners. Basically, everything in there. Just a couple other places. So I'll get on to that now. I was looking at some of your guys' work, and it looked like you're doing fairly well. I didn't check quite as in depth this time as I normally do, just because I figured, they know what they're doing pretty much. The signs all looked pretty good. I'm pretty proud of them, I'd say. Um, yeah, so we're just gonna keep going through this. Put that one there before I forget about it. Is equal. I could do that. There we go. Grab that circle, grab that line, set that tangent. We're going to get the trim tool again. We're going to trim off the top of that. And then this one too. So set those equal to each other. Grab that circle, set the tangent. Grab the trim tool, just kind of get rid of that outside edge. But since there's this construction line that prevents it from trimming all the way down, we're going to trim off that. All right. Gonna go back down here. Going to get rid of the trim tool for now. Let's set that tangent to there. That equal to that. Looks about good. Trim tool to get that down. Let's get over here. Oops. Tangent. All right. It's not equal to that. Come on. There we go. The trim tool. Cut that down. And we're just gonna keep doing the same down here. So now you might notice that, hey, like these circles here, they're pretty close together. So you might notice that these circles are pretty close together. So like the centers of them are fairly close, and like if you're looking at the final, it didn't extrude. I gotta go back and select the areas again because yeah. All right, so that should be all that. So you might notice like, hey, like there's barely any like like this could probably be done with just like a entire circle just slightly larger than the size we've been using so far. And yeah, I think that actually might look a bit better. So we're going to use that technique down here, where instead of setting the circle equal to the size of the previous ones, we're just going to set it tangent to these three lines. And one actually very cool thing, this is like a geometry type thing, but a circle, a circle can be like perfectly defined by 3 points. So if you take like any 3 points, there is only one circle that can go between all three of those points, as long as it's in a two-dimensional plane, which, since we're making a drawing, this is, we don't have to worry about any of that. So I have my first point down there, I have my second point right here, and I have my third point right there. And as you can see, the circle starts to turn black, which means that it is fully defined. We don't have to do anything else. So I can just pull out the trim tool, trim away that, trim away that, trim away that. Anything down there? Yep, there's something right here before it. Just trim that away. And yeah, we have a slightly larger circle, but it's a much nicer curve. Although it isn't quite stay consistent with how we've been doing it for the rest of the drawing. So we're going to that tangent there. Now we're going to make this equal to that. And then just trim that away. And now just about all we're going to have to do is make this symmetrical because our changes haven't fully carried over yet, you know. So let's see. Mirror, select a mirror line. We're going to go with z-axis. Now select all the entities we want to be mirrored. Let's go with this curve. So we got that. Then we need one down there. So let's do that curve. Select it. Selected it. Now we have to get that one down there. So we get that curve. Okay, got that. So now we just got to do all that. So select that. Select that. Select that. I got both of these. All right, that should be about it. So now we can go back and yep, we still have the issue with the parts not extruding because we didn't select them yet. So I'll go back into the extrude here, and says, and like here I could still add the spaces I want to extrude. So I'm just going to go click on all these. Take a couple seconds. We're gonna actually click all these. I'm a bit slow. Oh, that's not what I wanted to do. Click that again to get rid of it. Go back to selecting the small areas I want. All right, and that should be just about done. So now we have like a curved corner in each hole. So like this is a part that if you wanted to cut it on a like CNC or something, although it might be a tad hard right now because there's a couple holes that are missing, but like this would definitely be doable, just as reasonable. In fact, this is more or less the same method that our team uses to design parts that we are going to cut on the CNC. But now we have to make the holes. So you may notice that if I show the sketch again, that there's all these like large circles here, and I like intentionally left a point at the center of each one, or well, I used the circle tool, which creates a point at the center by default. However, the like point being there is completely intentional. I really wanted that to be there. Um, and that's because it makes it super easy to use the hole tool, and then I just have to select the like type of hole I want. So I want a nice simple hole, just a cylinder that gets cut out, and then I want it to be a through hole because I want it to go all the way through the entire part. Back to the front. And then since I am using an imperial bolt, a number 10, I want to select ANSI, not ISO or dinner PEM. I'm not actually entirely sure what those are. They're not as common, I don't think. And then I'll go with a clearance hole for now, so I can just put it right through. I don't want these to be tapped, I don't think, and I don't know, drilled. Free fit, yeah, that sounds about good to me. So that sounds pretty good. All we gotta do now is select the sketch points where we want to place the holes. So I'm gonna select that corner there, that hole there, corner there, hole there, 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 and that there. All right, so that should be just about every single hole I need to get, I think. And if yeah, I can hide that sketch now. And look, this plate's more or less done. Now, again, I've said this before. I'll say it again. Uh, these holes in the corner up here, where there's not really too much material between the. Does it say how much there is? Yeah, there's about like zero point 0.1 inches of this. Like that's not a very, or that's not the best way to design this. There are better ways, I assure you. This is just pretty quick, I guess. Um, so a hole more like this, where it has a proper distance between the, yeah, there we go, minimum distance. So like closer to zero point 0.2 is probably pretty good. I did it again. But basically, it doesn't hurt to have too much like extra space around a hole. However, if you don't have enough material around a hole, especially if it's like a bolt or axle or something that'll be under a lot of stress, that's it might be a bit of a problem at times. Um, but yeah, so now that we have our plate, there's just two other parts we need to make. However, before I start to work on those parts, since I want to know, like, oh yeah, uh, um, this part is this one part that I want. I am going to go down to the bottom left of the screen, and there's an area that says parts. Um, Currently, the only part I have there is part one, but that's not a very descriptive name. So I can right click on that and I can press rename. And I want this to be, let's call it faceplate. That sounds like a nice name to me. Um, so I'll just name that faceplate. And now I know, okay, yeah, it's exactly what part I need it to be. This is pretty useful if like I have multiple parts in the same part studio, which is what we'll be doing today. Um, and I need to like differentiate between each one. But so now that I have that part named, I want to create standoffs. And there's a certain design constraint I'm going to give myself. Um, the inner diameter of the standoff has to have, or it has to be a hole with the same diameter of like this hole here. And then I'm awful on shape. Um, and then since I want the spacers to like fit in nicely, I want the outer diameter to be the same as that curve right there, since that's just like a circular curve. Um, and to do that, I am going to use the front of this plate as my sketch area. Um, and I could just like draw on the plate. So the center of this curve on shape should just like automatically go like, oh, you're trying to create a feature at the center of uh, this curve, so I'll just let you snap to it by default. So I could create this to about any size I want. However, you might notice like, oh, it doesn't really, um, yeah, sometimes it can be a little temperamental. However, in this case, since I have this line going out to here, I'll just press tangent and it's now the same size as that curve. Okay, this is great. So we have uh, we have a sketch for a spacer with an, or a standoff with an outer diameter that won't extend beyond the uh, gearbox at all. However, we want the smaller circle here to be the inner diameter of our standoff, so we can just put the same bolt through. Now, one option here, or well, actually, these are probably both valid options. Um, so there's two ways of doing this. You can create another hole inside here, and and just have that circle be the same size as this hole in the faceplate there. Or since we know we used a number 10 bolt with all the settings we wanted, we could just create a cylinder and use the hole tool to just drill a hole through the entire thing. However, um, in this case, well, so I have this plate and I'll be using number 10 bolts. However, what if I might end up changing that for some reason? Now, in practice, I probably wouldn't. Number 10 bolts are pretty common for this type of thing. However, what if they do? I want to make sure that the inner diameter of my standoff is always the same as the diameter of the holes for the bolts in this plate. So in this case, I'll just be drawing the sketch with a circle, and I'll be setting that circle and that circle tangent to each other. I think that's how, yeah. Um, so that way I don't have to worry about like the bolt sizes we're using changing and then having to go back to change the standoffs as well. So for now, since that sounds about good, I'll just extrude this. And now you might notice that it's trying to add on to the faceplate part. That's not what I want. I want to create a new part for my standoffs. So I have to go up here, and instead of the add option, I have to go over to the new option. And you'll notice that this will change the color of the extrusion. So I can just go like, oh yeah, okay, that's a new part. That's all I need. And then, did I forget to, hold on a second. Okay, so the one dimension I forgot to get off of, all right, so how long are the standoffs? 1.25 inches, okay. So I had to like, so when I was like first designing this, I think I put the standoff length at 1.5 inches, and then I noticed like after I had put together the entire assembly, oh, it doesn't need to be 1.5 inches. It just has to be an 1.25 inches. So just go with 1.25 inches, or if I want to do it this the smart math way, I can just go 5/4 because that's 1 1/4. And so that'll set the length to 1.25 inches. So I have my new part. It's a standoff, goes right to there. This might not be a perfectly realistic standoff. I'm not sure how many standoffs you'll find have a um, have a like 0.1 inch wall, but did it get? Yeah, I don't know. Let's just say this is a custom standoff for now because we're like I don't know. It's just for now. I'm just going to pretend we have the capabilities to make custom standoffs. But so anyway, since this part, we want to make sure it's named something. We want this part. Let's just call it standoff. It makes sense. Yeah, I need to get over that. But okay, so now that we have that, we still need to make the thunder hex. stand-in. Now, this isn't perfect. I didn't design ThunderHex myself, of course. That would actually probably be fairly obvious. So basically, I don't know the exact dimensions. I'm a fool. Okay, here we go. And or yeah, so I don't know the exact dimensions. I just found like a like forum post online that said, oh, like this is this dimension, and then I know from experience that the actual hex part of ThunderHex. Oh, uh, in case anyone doesn't know what ThunderHex is, she might not. It's like a sort of specialized type of hex, I think. So basically, it's so like here is an example of normal hex. This is not ThunderHex. And like you can tell it's hex shaft because it has like the nice sharp edges and well, it's a hexagon. However, ThunderHex, it's like it has rounded corners. Now, this might sound like kind of strange at first, like, oh, why would you need that? However, it's really nice because it means you can. That's a bad example of it. There's probably a better example somewhere down here. I'm not gonna find it too soon there, but basically, it means that, or it allows you to to put a like hexagonal shaft in a circular bearing, and you don't have to worry about like, oh, maybe when they cut this hex bearing, it's like slightly off because a circular bearing, it's actually far easier to make a perfectly centered circle than it is to make a perfectly centered hexagonal cut. And yeah, it just makes it so much easier to deal with. I love ThunderHex so much. But anyway, yeah, so it has some kind of confusion. Yeah, if I could speak, it has some kind of confusing dimensions. So while the dimensions of the hexagon are also is 0.503 inches, which there might be a better like equivalent for that. I'm not very good at non-whole inch measurements, or actually just anything that's not an increment of like 1/16 of an inch. That's what the smallest I can go properly. Um, but then, okay, yeah. So the actual hexagon part, since you can put a half-inch wrench around it, that's just about slightly over 0.5 inches. However, the circular part, it's actually 13.75 millimeters, which it's a little. I'm not exactly sure why it's metric. It just is. But like, yeah, that's ThunderHex. I don't know. It's weird, I guess. Um, but yeah. So anyway, now when we're going to extrude this, how I also need to deselect all the edges because, well, I'm trying to like cut away at this, not build onto it with the. What are you loading for? Come on, there we go. Okay, so I have more or less my ThunderHex now. But now, how long do I need this to be? Okay, so we could do some relatively quick, just mental experiments to figure out how long this needs to be. So our plates, you may remember from last class, were extruded out to be 1/4 of an inch thick. We have 2 of those. So that means at the very minimum, our thunder hex has to be 1/2 an inch long because, quarter plus a quarter is half. So then we also need to make sure that since this does need to get from one side of the plate to the other side of the other plate that we're going to have over here, we also have to add onto that the length of this spacer. So you might remember that, or well, hopefully you can remember that we just made this spacer to be 1 1/4 inches long. So that means that the minimum length for our thunder hex is going to be 1 3/4. Yeah, 1 3/4 inches. So 1.75. That's about that long. So that's also just how thick our gearbox is going to be. However, this is relatively unrealistic. So yeah, we have this, but this just means that we have this shaft turning inside the gearbox, but nothing's getting out of there. We're not actually using this for anything. So in our case, since all we really need is to have the inside of the gearbox, like we don't need to just keep going, make it realistic. I could just kind of stop it there because, yeah, a better way to phrase this is more or less just a practice one. I could stop here, however, just in case, I am going to extend out an inch. All right, so we have our stuff out here, and this is more or less the same way we are going to have these parts in the actual assembly. But so I'll rename this, just call it Thunder Hex. Stand in. Since we don't have actual Thunder Hex as a model, this will do. And yes, so we're pretty much done here if we want. Since Thunder Hex, it's always black, we can edit the appearance. Let's go here. Let's 20, 20, 20. Does that sound right? I think that's a little too dark. 30, 30, 30. All right. Still a bit dark, but I think it looks nice, I guess. And then since our faceplate, this will be aluminum, most likely. Set that to I'd say that's a nice color. And then the standoff, this one could be more or less anything. I'll just material. Although actually, if you do have a material, it's pretty helpful sometimes. We'll just set this as like a nice light color. Actually, while we're here, assign material. Do they have 6061 T6? They do. There's just 6061. But yeah, you can like set materials if you want to do that for some reason. You might not have to, or you probably won't have to, but it just feels nice sometimes. So anyway, now we need to work on the actual assembly. We have pretty much everything done. We just need to actually start like putting this into an actual model of a gearbox. So how do we do this? you'll see at the very bottom of Onshape, I think Dexter already went over this in a previous lesson, but just in case. Um, we have the part studio, and then we have the assembly. In fact, you could actually create more. So say I wanted to create another part studio, I could do that. Or if I wanted a folder, I could like name that something. Probably use my folder. Um, can be a little annoying sometimes, but I don't need that part studio. I don't need this folder. Let me delete the folder. It won't let me delete the folder. Oh, that's fun. Oh, there we go. Just unpack. Okay. Um, but so we'll go over to assembly one, and this is where we're going to make our model. So our assembly. So first, there's the parts we created in Part Studio 1. How many of these are we going to need? Well, first of all, we're definitely going to need 2 faceplates. So I'll just start off by bringing in 2 of those. I'll put them some distance apart. And then we're also going to need a bunch of spacers. Um, so like these holes here, these are for the motor. So we don't have to put a spacer there, but we still need one for here, a second one for here, a third one for here, fourth one for there, and a fifth one for up to, my mouse is freaking out. So basically we need 5 spacers. Okay, we're gonna, or standoffs. So we're gonna bring in 5 standoffs. But okay. So we have that, and then since we only need 1 output shaft, we're only just going to bring in 1 piece of thunder hex. So that's great and all, but that's not everything that we need. There's still more stuff. So now we have to go over to the other documents page, and we are going to search for MKCAD. I think we went over this previously too, but MKCAD is a great library. It's full of all kinds of stuff that you might need for first. Um, so in this case, since we're trying to find first, we're going to find 2 Neo brushless motors. So it's not in electronics. It's obviously not in like sprockets, pneumatics, wheels, all that. I keep going, not in electronics. Here we go, motors. So this here has pretty much all the motor stuff that we need. And or well, most, not all, I suppose. So there's like there's like a 77.5 Pro, a bag. It's actually been a really long time since I've seen one of those. They're fun. I like them. There's like a Sim, a Falcon 500, a Neo 550. These are actually pretty nice, gotta say. And then yeah, there's also the Neo brushless motor, and this is the one I want. So I'll just bring in 2 of these. All right. And then now that I have my motors, I need the gears that are going to go on them. So I'm going to go back to my MKCAD search, and once it loads, somewhere in here it'll say gears, I think. Yeah, here we go. So MKCAD gears. There's also sprockets. Sprockets are different. Sometimes we want those, but we don't want them right now because a sprocket is used for driving chain, while a gear is used for driving another gear. But so anyway, we're going to go into gears, and then we want an 11 tooth gear. So there's 2 of these. I don't actually know what the difference is. I do know I want. Wait, which one do I want? a different number. It's a 10 teeth. That might be why. Yeah, okay. So this is the one I want. Actually, what's the difference with that one? Oh, that one has like another gear on the inside. Yeah. So that might be useful for something, but we don't need it right now. Undo, there we go. All right. So is that, yeah, that's the right one. So we have both of the gears we're going to need there. Um, and now, since our gear ratio is 11 teeth here to 52 teeth on the larger one, I'm gonna have to find the 52 tooth one. Now that could be a lot of scrolling. I don't know where it is, so I'll just type 52 in the search bar, and look, so we get two 52 tooth gears. Now you may say, why two? Um, well, there's the first one, which is a half-inch hex bore, which is the one we want. But then there's also the second one, a 3/8 inch hex bore. Um, we're going to be using the 1/2 inch. However, the 3/8 inch is pretty similar. It just uses like a smaller shaft. If like your mentor wants to use a smaller shaft, they like it works. Usually, you would be using a 1/2 inch shaft or just 0.5 inch, like we're going to be using now. However, 3/8 inch can be a valid option. It might depend on like the situation. So anyway, now we have almost everything we need, except now we have to actually find bearings to make sure that um, this shaft and this gear can turn properly. Um, so now you may notice, like, okay, so there's these holes in the plate. Those correspond to like these. Someone's coming to me. To like these like smaller circles, smaller circles, uh, to these like extensions off of the motor. So that will let these fit perfectly. However, well, like that's why they're so small. However, this here is a lot larger. That's because it's designed um, for a proper bearing. So we are going to scroll through here for the MKCAD bearings. And then there's a bunch of different bearings here. However, there's one specific one that we're trying to find. We are trying to find one with a thunder hex inner diameter and an outer diameter of 1.125 inches. And we also probably want it to be flanged while we're at it. So now, what do all those things mean? First one, the thunder hex inner diameter. That means that the inner diameter of the bearing is sized just perfectly, so that this like 13.75 millimeter circle will fit perfectly inside it, which means that, yeah, I could more or less use the thunder hex as a circular shaft. Even though it's hex, so I can also put 1/2 inch hex stuff on it, like here. And then the 1.125 outer diameter, well, a bearing, it needs to have like some like space around the outside, or like around the outside of the like hole in the center, so that it can actually like spin. There's actually like a bearing there, and that's just, and 1.125 inches is just the like standard size used for that kind of bearing, I guess. Basically, it just gives it enough room. It, as far as I know, it's just the way the part is. If someone else has a like knows the reason why, feel free to speak up. But I don't know. It just is. It's just like that's one of the things you kind of have to know. But then you might be saying like, okay, flanged bearing. What does that mean? Why is that special? Why do I want that? A flanged bearing means there's like a wing that kind of goes around the outside. It's a flange. Um, so if I bring in one of these bearings now, you'll see that, yeah, like, so around here, there's like this small lip that goes over the top, and that stops it from going in too far or like, it only, like, or it helps keep it at the position it's supposed to be at. So if I bring in a radial bearing, you'll, if I place it, you'll see that, yeah, so these two bearings are pretty much the exact same. However, this one, it might like work its way through to the wrong side or something, where this one, we don't have to worry about that. It's just kind of perfectly, like, yeah, it won't like get like pushed through the wrong way or something. So we are going to want two of these here today. Um, Actually, I forget exactly what orientation I had these in, so I'm going to go check that right now. Gearbox. Okay, that makes sense. All right, so now that we have all the parts that we are going to need, we have both of our motors, we have both of the pinions for the motors, we have all of our spacers, we have both of our faceplates, we have a bearing for each faceplate, and we have our shaft that's going to go all the way through. Now that we have everything we need, we can press the check. And if we need to bring this back up later, say like, oh no, I forgot to add in a standoff, I can just go to the top left up here, click insert. I can just go get another piece I need. It's exactly the same thing we were in before. But now I can start working. So I, for simplicity's sake, or just so it doesn't get dragged around while I'm working on it, I am going to attempt to make this to the origin. This might be difficult. It can be a little temperamental sometimes, but so I'm gonna go up here and I'm going to grab a fastened mate. You can also just press M. Um, this is what I meant about it being kind of temperamental. It doesn't want to. This, oh, where'd it go? There it is. Okay, so I could do it that way, I guess. Um, but yeah, so I have that, and then I want to mate that to. So it's working perfectly. Like, yeah, okay. All right, so I've done that now. So if I get out of the fasten mate, you'll see that like if I try to move that around, I can't. I can still move everything else. So this is nice, so it doesn't like move around weirdly when I'm trying to work on it. It just keeps it nice and centered. It's more of just like a feels nice thing. Anything else, I don't really actually need to do that. I just like to because I don't like things moving around in weird ways. Um, So now we are going to start by, yeah, these motors. Let's start with the motors. That sounds pretty good to me. So you might notice like, okay, for the sketch, if I press M, or for the sketch, for the faceplate, I can access the mate connector in the center um, by just hovering my mouse over the circle itself. So that works perfectly fine. However, how exactly do I want to do it here? Well, whoever created these models was very kind to us, and they actually left us a visible mate connector right there. In fact, if you actually hover your mouse over the outside body part, you can kind of find the other ones. Um, there's a bunch of these everywhere. But they were really nice, and they just included one that's visible by default. So I can just kind of click that, and I did that. Did I do that wrong? No, I did that right. Okay, I'm not dumb, I hope. um, and yeah, so anyway, if I click the mate connector on the motor and the mate connector on the faceplate, they get mated together and solve that. And it's perfectly flush against that surface. It's not rotated properly, but so this is one of the things where when you're actually building it, it's like, oh yeah, well, I know that has to be aligned with that hole. This is just one of the things where do I need to put it in the model? Probably not. Although I suppose it would help if you're too confused. Because wiring and stuff, the wire has to come out somewhere and it goes. We're actually speaking of that. Uh, in this case, since the wiring would definitely interfere with that bolt, it's like, oh crap, I just noticed that this isn't right. I need to fix it, actually make sure I can put in that bolt. So I need to find the mate that connected that to the faceplate. In this case, it was fastened 2 because we have fastened 1 connecting us to the origin. So I'll go into fasten 2. I'll double click on it to pull up the dialog for it. It's like, okay, well, I can see that this is going out there, but I don't want that. So um, in the bottom left of the fasten 2 dialog, there's a small option that says reorient secondary axis. That's a really complicated way of saying just turn the thing 90 degrees. So if I press that, you'll see, okay, look, so now my wiring, it comes out up there, and that's perfectly fine. It's exactly where I want it to be. It won't really conflict with anything else. I don't have to worry about that. So that's all good. Then I need to put in my second motor. Just let's take this. I mean, this is more or less the same thing as before. So it's been too fancy to do there. And then our wires, they're already coming out in a perfectly fine place. So solve that. Okay, so we have that attached. Get you out of the way. So now let's put on the standoffs. We need these to be centered on these holes, which is a conveniently provided bait connector. So we're just gonna start with putting one here. Let's go with this one. Sounds good to me. Put one here. I can select it. And then, yeah, you might notice, like, oh, I could just click on the outside and it works perfectly. So, okay, got that there. Put another one. Oops. I don't know what I did. Oh, it's up there. Nope, I don't want that. That's not what I wanted. I'll hit cancel. And then I'll just go back in. I can either click the button or I can just press M to open up the dialog. So let's grab that one, put you right there. Sounds good. So I'll press the check mark. Let's grab that one, put it right there. That one, right there. Okay, so I have that done now. However, there's still some more stuff I want to like work on in there, so I'm not going to put the faceplate on quite yet. So let's just hide that for now. So I want to put this bearing in that hole, and then I want to attach these gears, or these pinion gears to like that shaft there. Oh, you can do a gear relation. I didn't notice that until just now. I really wish I saw that earlier, because that's actually pretty cool, not gonna lie. So anyway, we have like this here. I want that to turn. Like if I just did a fasten mate, I could like select, let's take this shaft, we're gonna put it halfway through, and then we're gonna halfway on the gear. All right, so like that would work. However, this isn't exactly what we want, because like it's a gear, it's supposed to turn. But here it doesn't turn, it's just kind of locked in place. There's not much we can really do about it. So a way I can fix that is another tool called a revolute mate. It works pretty much the exact same way. In fact, I'm pretty sure this was a key point of Dexter's presentation when he was going over the types of mates. So we can add that on, and it turns, but it doesn't go back and forth on the shaft, which is exactly what we want. This is perfect. So now up here, I can do pretty much the same thing, just kind of go for a revolute mate. We're gonna put that about halfway through there. Looks right. And then since I'm trying to put this like centered on there, I'll just kind of, and we're done. So now both of these will turn, which is really nice. I don't have to worry about like fancy, yeah. So that works perfectly, but then I need to put this bearing in. The bearings are a little tricky times. I'm gonna, you know what? I'll use a revolute mate for this one too, because it'll be a little easier for later on. So like, there's no good way to like select exactly where you want the mate to be, because like if you look at this, there's like all these different points on there. I think probably the best way I can position the camera in a way where this can actually be understood. So since like the flange of the bearing, like that part there, this is the part that's going to be flush up with the surface of the faceplate. I can just kind of click on there, and then since it's a circle, it'll automatically select the center point of the circle as the like mate. And then from there, all I have to do is just say, okay, I want it to, you know, that circle there. And yep, that looks right to me. flush with that. Flush there. Yep. That looks like it's been put in properly to me. So next, do I want to do that yet? Yeah, I'm gonna do that now. So now I'm actually going to put this hex shaft here in the. That. And then, like, oh no, there's a lot of different levels. It probably doesn't matter quite as much for this one. I'm just gonna choose that there. That looks about right to me. It like, because like at super small distances like that, it probably doesn't matter quite as much. It's just like a this looks right, this doesn't look right type thing. So okay, we have that now. But now I need to get this gear in here. How do I do that? Well, pretty much the same way we've been doing everything. I'm gonna grab that bait. And then I'm also, well, since I want this to be like offset a certain distance from the inside of, or like from like lip part of this variant, I'm going to click on the top circle there. And then by default, it just pushes it like flush up against it, which is actually not that bad. I see some Z fighting in there, so it's very likely that that's like perfectly, like exactly where it needs to be. However, it's a little too close for me, and I'm not sure I want my gear to be rubbing up against my Barian. In practice, I'd probably put like a eighth inch spacer or like a quarter inch spacer, maybe. Probably just an eighth inch, but we could simulate that. So since the z-axis of the mate is the one we want to be affecting, since you can see it like here in the like mate thing, I could just say, okay, I want that to be an eighth inch off, and look, it made it closer. That's not really what I want. I don't like that. So instead, I can put a negative in front of that, and I'm an eighth inch off now. Okay, this is perfect. So just like that, oh, it's not aligned. This is it. There we go. That looks right. Okay. Yeah. So that's perfect now. Now all I have to do is attach this to there. So like, yeah, first I probably want to put my Barian in, because you know it'll be a pain to do that if I'm trying to like work on it while it's like, I don't know if I can grab this again. Because if I'm trying to like work on it, like it's kind of hard to, yeah. So just like if you were building this in real life, we're gonna put Barian in first. In this case, since I want this side to be the one facing in, that's just simple, I guess, or it's fairly easy. When I'm going to do my fasten bait, I can select the. I'm going to grab that same lip as last time, and I'll grab that. Just, yeah, it looks right. And then so you may have noticed that at first, hey, the buried sticking out and part of it's embedded inside the plate. That doesn't look right. I don't like that. That's impossible. If like one part isn't in the orientation it's supposed to be, there's this button here or up there. It says flip primary axis, and what that does is it just like it inverts the part, which for now, yeah, it's exactly what I need. So now that bearing it's exactly where it's supposed to be. And now we can just model this into here. Um, so I need to find somewhere to attach it. I'll just grab that little spot down there, this one here, and that didn't work. Why did that not work? I don't think I selected it. There we go. I didn't actually click, I guess. It's fun. Why is that not? Yeah, okay, there we go. So now, once we accept the bait, you can see that the part just went right over to there. And yeah, this is exactly what we want our gearbox is done. You see, like, that turns. If we wanted to, we could add a gear or relation between, like, that gear and that gear and that gear and that gear. But yeah, no, this is pretty much exactly what we want. As you see, we might be able to, like, so say, like, oh yeah, that's might not be right. We could probably cut this down a quarter inch, and actually, yeah, okay. So see here, there's like tons of space. Maybe this is too much space. I can make this smaller. I'm going to go into Part Studio One by standoffs. Maybe I don't want them to be an inch and a quarter. I just want them to be 1 inch. So they're tad bit shorter. I go back to assembly one and it's changed. And yeah, it's a much smaller object now. So the one word of advice, um, the pinions like this, you should probably have something to, like, stop them from going, or okay, yeah, so this is bad design, kind of, because this here kind of don't want, like, or because first of all, that hole is smaller than the pinion, so after a while it can just kind of, like, work its way out in practice. Um, or if the hole is, like, small enough for this axle but too small for the pinion, it'll be like rubbing up against the plate, and that's not very fun. So you might end up just, or yeah. So basically, this design is not perfect. In practice, you would use, like, something to stop this from sliding down the axle. There are things like that that do exist. I forget what they're called, which is a bit of a problem. But yeah, so this is more or less it. Hold on, let me. Spline lock? I gotta look it up. Maybe. I don't know. All kinds of stuff. So anyway, now that we have that, um, yeah, so this is our completed gearbox. So now we'll be going back to our presentation. We only have 10 minutes. It actually took a little longer than we were expecting, which is kind of interesting, I guess. I don't know. Um, so back to here. So we've done all this. So now I'll turn the present, or, oh, actually, no. Is there anything anyone didn't understand about the gearbox? Anything I can clarify about why I, like, designed something the way I did? Anyone? Anyone at all, or should I just keep going?
I understood it, sir.
Oh, thank you, thank you. All right, so um, since it doesn't seem that there's any questions, unless someone's typing something out, um, I you did so good that there are no questions. Ah, thank you, Majdi, very much. Um, so we'll move on to the West Coast Drive chassis. This part will be taught by our lovely presenter, Dexter.
Yes. Hello. Okay, so fortunately we don't have time to begin doing the actual CAD process for the West Coast Drive chassis today. So instead, this can be a bit of a preview for the lesson on Wednesday. And so, West Coast Drive chassis, as is in the title, is a type of chassis commonly used in the first robotics competition. And so, as a chassis, it functions as a way to mount everything in your robot, hold your transmissions, hold your wheels. Basically, it's the base of the robot, everything is built off of it. And so, a West Coast Drive chassis is a bit different from some other chassis in the ways that the front and back wheels are connected to the middle wheels that hold the transmission. That's really the main difference. To be frank, the definition of a West Coast Drive chassis can be a bit vague, but it's speaking a fairly simple form of chassis. And so, like with any other chassis, when you're designing one, you have a few things to consider. The first one being how wide and how long do you want your chassis to be? So you need to make sure that anything you're designing with a chassis, the dimensions are within the constraints available or the dimensions that you want. And you need to make sure to compensate for the width of the rails added to the length of other rails. For example, this chassis in the picture has a side railing, which is this railing that contains the wheels, and then the front and rear railing. And the width of the front and rear railing will be combined, of course, with the side railing length. And so you need to keep that in mind as you're planning and designing out these chassis. Um, Additionally, some of things to consider, you're going to want to make sure that your wheels have enough clearance. You're going to want to make sure that the rails have adequate mounting holes in order to mount your transmission or other components that you might want. For example, in this West Coast Drive chassis in the picture, there's a bunch of different mounting holes scattered on the aluminum railings, and those allows us to mount the gussets which hold the rails together. It also allows us to mount the transmission, among other things. That empty box in the back of the design is a battery holder, and that's mounted to the chassis using those holes. And additionally, another part of the chassis you want to consider is the belly pan, which is that green option on the bottom. Belly pan will mount if you want your electronics or anything else that you might want to have mounted. And at least with this belly pan, we realized that our transmissions wouldn't be able to be mounted if the belly pan was just a solid sheet. So we had holes cut into the belly pan, and that gives the transmission clearance. So it's things like that you consider, but overall, a chassis design is fairly flexible. You can very easily modify it to suit whatever kind of needs that you might want. It's inherently very modular in that sense. So there's not really a wrong or conversely an optimal way to design a chassis. it really just depends on your situation. And so in regards to this chassis, our team has some extra things that we've added onto it. On the front and back railings, we have those triangular aluminum pieces. Those are our bumper supports. So this chassis has a bumper wrapping around it. In the designing process, we made sure that the bumper would be flush with the ends that stick out with regard to the front and the back railing, while not interfering with the wheels. So that was something that would have impacted what length we chose for the front and back railing. And then the other supports on the sides, left and right side of the chassis, those once again hold a similar purpose, and they are intentionally designed to match the distance that the front and back railings stick out from the chassis, or the chassis, but from where they meet with the side railings. So in the next lesson, we're going to be designing some portions of this. We're going to be designing the front and back railings, which are actually the same design. We'll also be designing the side railings, the belly pan, as well as the bumper supports, and then bringing it all together. So this is work with maybe a bit of a larger assembly, and should hopefully provide some valuable insight if you're in a situation where you're going to have to design a chassis of your own. So in which case, that is about all we probably have time for to cover today. There's some other things we could mention. For example, the West Coast Drive chassis, aluminum extrudes are 2 inches by 1 inches, which gives a bit more vertical space to work with. But that'll all be then saved for the next lesson. So, in which case,
if you want to leave now, you probably can. However, now it's time for the 10-minute quiz Q&A. We're probably not 10 minutes, I suppose.
quick
We just gotta have that
3-minute
there.
Q&A.
Yeah. So why do we use gear ratios? Does anyone know? Torque and speed, it looks like. Yep, that's pretty good. To change speed and torque. And yeah, so basically, when we want to increase the speed, we could use a gear ratio that does that at the or however it does prevent us from getting as much torque. Or if we want more torque, we can use a gear ratio that will give us more torque at the expense of speed. So what mate do we use for a rotating part? Rotational mate. Yeah, I mean, revolute. And yeah, that's it. And then, so there's plenty of types of mate. There's basically any mate you would ever need to use for any situation. In this case, yeah, rotating parts is revolute. Um, I was having a hard time coming up with questions last night, so that was one of them, I guess. What advantages do 1x2 stock provide over 1x1 stock? We didn't go over this in the proper lesson. However, you might have heard Dexter at the end talking like, yeah, the extra height makes it a bit easier to just work with sometimes, like, especially for a West Coast Drive chassis. Um, the gearbox, the shaft has to like go through the frame, and if we were only going to use like 1x1 stock, the like bearings or holes or whatever we're using might not fit. It just makes it so much better. So now, finally, does a 1:4 gear ratio make the output spin faster or slower? Anyone else? Faster, faster, faster. Darn, you're actually smart. Yeah. So so the one means that the input turns once, and then that one turn makes the output turn 4 times. Um, so yeah, it makes the output spin 4 times faster. So good job, everyone. Give yourselves a pat on the back or what have you. Class is pretty much done. You feel free to leave unless you have any questions. Me and Dexter will be staying here like last time. If anyone has a class-related question that they want answered that we can help with. But yeah, feel free to leave if you're done. It's pretty much it for today.
Thank you all for coming.
Yep. Thanks, everyone. Have a nice day.
I have a question.
Yes.
For the homework for today with the designing something, when you say design like a robot piece or a robot thing, what do you mean by like, do you have specific like specifications for it?
So we actually thought we were going to, or when we were creating the lesson, we didn't think that the gearbox part would take as long. So we thought there'd be a lot more, we thought that we could go into the like West Coast Drive design in much further detail than we did today. And the practice activity was partially based upon that. We might end up like adding something onto there. That'll actually probably be a pretty good thing for me and Dexter to talk about after the lesson. Yeah. But so anyway, as for any specifications, we were thinking that like a reasonable size, like probably something similar to what we were going to be designing. I'll just post some rough measurements on there.
Okay. Well, thank you for telling me that, because I was kind of having a few questions in my head. So.
Oh yeah, it's all right. Don't worry, we are entirely here to help you.
Thank you. So, thank you for the classes. These are very interesting and very detailed.
I mean, I'm glad to hear that they're interesting because thank you so much.
Welcome. Have a nice day.
Thanks, you too.